in the exercise session later on this morning, and that would be a chance to ask any questions. Anything you want to straighten out. So just as a quick reminder, what we did last time. So we're looking at homomorphisms. So we have spent a few lectures looking at isomorphisms. So these are special mappings from one group to another one. They're bijective mappings, so they're one-to-one and onto. So they're an exact mapping across the elements of one group, exactly paired with elements in another group. And if it satisfies this property, this kind of multiplication type property, or this property called the homomorphism property, then it turns out that that mapping is exactly respecting the group structure. And so if there was an isomorphism between two groups, it meant that the groups, they should be regarded as essentially the same as groups. They might be very different mathematical objects. One might be a group of permutations, the other one might be a group of matrices. For instance, one might be a group of functions from the real numbers to the real numbers, the other one might be some kind of group of number type objects. And so they can be quite different mathematical objects, but if you have this group mapping between their group structures, it can show you that they should be regarded as having essentially the same group structure. Now what we're looking at here in chapter 11 is where we weaken that condition that we ask for the mapping to be a bijection. If we don't ask for that, if we're willing to consider any mapping at all from one group to another one, from G to H, but as long as it satisfies this multiplicative type property, where phi of a product, so this product here, G1, G2, is a product of two elements in G. If phi of that element, whatever it is equal to phi of G1 times phi of G2. And this product here is, of course, taking place in H. So you're multiplying phi of G1, which lives in H, with phi of G2. If that multiplicative type property is always satisfied, then we call it a homomorphism. And indeed, this property can be called the homomorphism property. Okay. Now, because we've gotten rid of the bijective condition, if there is a homomorphism from one group to the other, it doesn't say that they have the same group structure. But what we'll learn about when we prove today the first isomorphism theorem, it does kind of tell you that something of the structure of G can be found somewhere within the group H. So not an exact copy of the group structure of G in H. It would be if your mapping is injective, but homomorphisms in general will not be are allowed to not be injective. So they can collapse sets of elements here down onto the one element in H. But when you do have a homomorphism from one group to another, it says something like, or you can kind of interpret it as saying something like that some aspect of the group structure of G can be found within some possibly smaller part of H, within some subgroup of H. And we'll tease out exactly what, we'll say exactly what we mean by that, and we'll make it very concrete, that vague statement, make that very concrete with our first isomorphism. So the examples, okay, I won't give the whole lecture. Again, I get trapped into that sometimes. He gave some basic examples here from some of the basic types of groups that we know about. And then what we spent some time on last time was proving proposition 11.4, which gathers together a lot of basic properties that are satisfied when there is a homomorphism between two groups. Very natural looking properties. A homomorphism must map the identity from the domain group to exactly the identity in the codomain group. Okay, so that says something about mapping one group structure onto another one. Any element G, what does phi do to the inverse of G? It must send it to the inverse of phi of G. Again, that's nice. Okay, again, that's saying that if you have a homomorphism, it must respect the group structure to some extent. Okay, it must send an inverse element to the inverse of wherever it sent the original element. Okay? Thirdly, if you've got a subgroup in G, then when you map it across to G2, so everybody, we're all happy with phi of a subset of G. Phi of a subset of G, just look, it's the subset in G2, which consists of phi of everything within H1. Okay, so if H1 is a subgroup of G1, then when you map it across into G2, you again have a subgroup. Okay? So again, that's saying maps group structure to group structure, just an example. And fourthly, and this is some kind of construction we maybe haven't seen before, is that when you start off with a subgroup in G2, so this H2 is a subgroup of G2, you can form this construction, which is phi inverse of H2. This is also known as this can be called the pullback of H2. Remember, phi does not have to be injective, so it's a little bit of an abuse of notation. We can't assume that there is an inverse function phi inverse. And we're not claiming there's an inverse function from G2 to G1 called phi inverse. However, we're using that notation, phi inverse. But we're not applying it to elements of H2, we're applying it to a subset of G2. And that can be defined perfectly well, no matter whether phi is injective or surjective. So phi inverse of H2 is just defined to be the set of everything in G1 that got sent into an element of H2. Okay? So you kind of have H2 within G2 subgroup, and you drag it back using phi. So you look at everything that got sent into that subgroup. It turns out, and we proved it last time, that has to be a subgroup of G1. Okay? So if you look at the subsets of G1 that are mapped onto subgroups in G2, those sets have to be subgroups themselves. So again, that's mapping subgroup structure to subgroup structure to some extent. And the final extra bit, if it happened that H2 was a normal subgroup of G2, then so does the pullback phi inverse of H2. That has to be normal in G1. Okay, we proved all those properties. And there are some similar properties in a similar spirit located in the exercises. And in particular, things like 8, 9, and 10. Those are properties that could have formed part of that lemma. These are basic group type properties that are preserved by homomorphisms. So if G is abelian, G is an abelian group, then if you fix an element, little g, no, hang on, sorry. G is an abelian group and you fix an exponent n, then raising to the power n is a group homomorphism. Maybe not 8, but 9 and 10 I was particularly looking at. Yeah, if you've got phi g to h, if G is abelian, phi of G, which is within H, a subgroup of H, that has to be abelian. And if you've got phi g to h of G happens to be cyclic, then the image of G, phi of G, which is a subgroup of H, that has to be a cyclic subgroup. Okay. Any questions so far on that material? So that was basically the review from last time. Have any questions based on that? Okay. So coming then to what we're going to look at today. So we begin by looking at the definition of kernel. So if phi, and I'm trying to stick to his notation, phi g to h is a homomorphism, so a group mapping. Then we can define this subset initially, kernel of phi, and this is the set of everything within G that gets sent to the identity. When I write phi of G equals E, it should be clear that what I'm meaning is that this E is the identity within H. Yeah, because phi is a mapping G to H. Phi of G, of course, lives in H. So if it's equal to E, I must be talking about the identity element. So this is the set of everything in G that gets sent to the identity element. Theorem 11.5 says this is a subgroup. Well, is a kernel of phi is a normal subgroup of G. Now we can give a proof of that, but we can do it in quite a clever way. We don't have to get going again and engage with the definition of normality and look at combinations of elements. We've actually proved something. We've actually proved all the necessary steps for this already. Because notice that we can express kernel of phi as a pullback of a certain type. You can write kernel of phi as phi inverse of the set consisting of the identity. Okay, so the set consisting of just the identity, this is the trivial subgroup within H. It's a subgroup, it's a perfectly good subgroup within H. Not particularly interesting, it's just got one thing in it. But the kernel of phi is clearly the pullback of this. Okay, so it's the set of everything in G that got sent into this. Well, there's only one thing here, so it's the set of everything in G that is in that phi of G is equal to the identity. So certainly, and we've already proved that pullbacks of subgroups are subgroups. And additionally, we also proved that pullbacks of normal subgroups are normal subgroups. And the trivial subgroup is always a normal subgroup within whatever group it's in. Remember, the condition for normality was that the left coset of the subgroup was always the same as the corresponding right coset. Well, if you form a left coset of this, if you multiply this by a little element H, well, it's just a subset consisting of H. And that's clearly the same as if you multiply this subgroup by H on the right. You just end up with H. And this is the trivial subgroup of H. Also, it's normal in H. So by 11.4, proposition 11.4, which we just proved, the kernel of phi is normal in G. So that's a nice way of proving that. It makes good, efficient use of the proposition that we've already gone to the trouble of proving, and just some basic facts about the trivial subgroup. Okay. But you could also go back to arguing on the level of elements and cosets, from the beginning, and you'd be able to, write out the proof of that without any, without too much bother about it. So that immediately leads us to the idea of factor groups. Okay? If the kernel of a homomorphism is a normal subgroup, that means we can factor G by the kernel. And what we're going to come on to now is the first isomorphism theorem. The first isomorphism theorem tells us what that factor group is, and it links it to the homomorphism, ties it into the homomorphism, and ties all these different or closely associated concepts together. Okay. Any questions about that? First of all, that proof of normality of the kernel, is that okay? So the kernel is an interesting thing to look at. It gathers together everything that was collapsed onto the identity. And in some way, the kernel is a measure of how much information about G is lost by the homomorphism. Okay? Because you're gathering in the kernel, you're gathering together all these elements of G, and if the kernel is got lots of things in it, so if it has, then you're gathering a lot of the elements of G, and these are all the ones that are all collapsed down on top of the identity. So when you look at the image of G under the homomorphism, all those elements have been collapsed onto the trivial elements in H. So whatever information there was in the distinct elements there within the kernel, whatever mathematical structure there was about what these elements were and how they were related to each other, that's all been lost when you suddenly collapse them all down and call them the trivial element. Collapse them all down on top of the trivial element. So that's the way to think about the kernel. If the kernel is small, it means we're not losing that much information about H when we apply a homomorphism to it. But if the kernel is large, a large subgroup of G, that means you're pushing an awful lot of stuff and collapsing it down onto the identity element in H. So you're losing a lot of information about H. When the kernel is a small, I mean, you could spend ages talking about this. If the kernel, well, let's do it. If the kernel, how small could the kernel be? What would be the smallest possibility for the kernel? We're not quite onto the first isomorphism theorem yet. What would be the smallest subset of the kernel could be? It's a subset of G, remember? Phi is sending G to H. Well, we know a homomorphism has to send the identity element to the identity element. So the identity element has to be in the kernel. But nothing else, you know, this could be the kernel of some isomorphism, some homomorphism from G to H. If the kernel is equal to the identity, then that implies that phi is 1-to-1. Phi is 1-to-1. Okay. True. Yes, because I think we can do this by proving the contrapositive. If phi is not 1-to-1, then there exists G1, little g1, and a little g2, such that phi of g1 is equal to phi of g2, but g1 is not equal to g2. That's why that's how a mapping can be not 1-to-1. So we want to prove that if that's the case, then there must be something non-trivial within the kernel. And so how do we send something to the identity element? We could multiply both sides by the inverse of G2, and we get the identity. But then that implies that phi of G1 times phi of G2 inverse is equal to the identity. But then that would imply that phi of G1 G2 inverse is equal to the identity. So that would imply that G1 G2 inverse is an element of the kernel. Phi. Yes, 5G. Yeah. Well, I was only slightly worrying there is how do I know that G1, G2 inverse is not just the identity element again? Have I actually found something non-trivial that's in the kernel? Yeah, I think I have, because you just have to note that the fact that G1 is not equal to G2 implies that G2 inverse is not equal to G1 inverse. Two elements are different, then they can't have the same, because that would imply that the two elements have to be the same. The inverse of two elements are the same. You just take the inverse of both sides, and you get that the two elements are the same. Okay, so if you've got two elements that are different, they have to have different inverses. So if G2 inverse is not the inverse of G1, then G2 inverse times G1 is not the identity. So G1, G2 inverse is not equal to the identity, and G1, G2 inverse is an element of the kernel. So that's the contrapositive of that claim that I made first. The statement, if phi is not one-to-one, then the kernel is not just consisting of the identity element. Here's a non-identity element, G1, G2 inverse, that is in the kernel. So if you look at the contrapositive of that, that's this original statement. If the kernel is trivial, then phi is a one-to-one function. Phi is injective. Okay. So that's just a slight detour. So now let's come to our first isomorphism theorem. So here we have, and I'll stick to his notation, I think he changes the notation slightly. So he's got a group G and a group H and a homomorphism psi between. Okay, so psi is a homomorphic mapping from G to H. And then we've got the kernel of phi will be a normal subgroup within G. And we can be a normal subgroup within G, so we'll be able to form this factor group. And so we're interested in linking this factor group back to the homomorphism psi. Now within H will be a subgroup of H, which is phi of G. Okay, so that's the subgroup symbol. This U is like a sideways subgroup symbol. So phi of G is a subgroup within H, the image of G under psi. Now we may be, psi is a homomorphism, so it may be taking different elements in G and collapsing them down onto single elements in H. So it might be losing information about G. But if we want to think about, if we want to know, so if phi might be losing information about G, but phi of G is still a subgroup within H. So what's the how does phi of G relate back to the group G? Well, it's possibly a simpler group in a way, a group with less structure, less rich structure than G, because phi can collapse different things in G down onto the same thing in H, so it can lose information. And it turns out, what we're going to prove now is that this subgroup of H, in a very natural way, can be seen to be isomorphic to this factor group. So that makes it quite concrete in saying, so this is an isomorphism mapping, that when we said before that the kernel of a homomorphism describes the information that's lost in the homomorphism. So when you form this factor group, G, quotiented out by the kernel of psi, sorry, you get a group that's related to G. It's built out of cosets of G. And when we were discussing factor groups before, we explained how these factor groups can be seen to, be slightly simpler groups than the original group G. Lost some information about G, but still telling you something about the group G. But what it is then, it's going to be exactly isomorphic to the image of G in H. Now, what are these mappings here that we're going to construct in this theorem and talk about? So this mapping here is eta. This is the Greek letter eta. That's going to be an isomorphism. Eta. Greek letter. And this mapping here is going to be phi. Phi is known as the canonical homomorphism from a group G to a factor group G. This is when we say canonical, this is another example where I did it before. Remember, I might metaphorically hold a gun to your head and ask you to give me a definition of something. And if I force an answer out of you, it's the most obvious thing to say. So there is always a nice, well-defined, most obvious choice of a homomorphism that you can have from any group to any factor group of that group. Okay, so here we're talking in particular about the kernel side. Now, why do I say it's so obvious and simple? I mean, this, you know, surely it's not obvious and simple or direct, but really when you think about it, it is. If I want a mapping phi from a group G to a factor group of G, so what's the value of phi of G? Well, if it's an element of the factor group, it has to be a coset, yeah, because the elements are cosets. So it's going to be some coset. So here's the subgroup that we're talking about, the kernel of psi. I'll just put brackets around it to indicate that that's that one thing. And it has to be a, okay, we by convention, the default we talk about left cosets. It's a normal subgroup, so left coset is the same as the right coset, but we'll just write it down as a left coset. So what we're missing at the moment to complete this definition is the element that we put here. So what element am I going to put there? And you know, if the clock is ticking down and the bomb's about to go off and you have to give an answer, what answer would you give for, like, which group element of G, which coset, which group element of G am I going to put here? Which coset am I going to associate to the element little g? And it'd be strange to do anything else except make it the coset corresponding to G. Yeah? What we're trying to define a function from the group capital G to here. So we have to decide, we have to have some way of assigning values to every element, you know, to any element little g from here. The value, the type of thing it has to be, well, it's in the factor group, so it has to be some kind of left coset of the kernel. There's the kernel. So which left coset are we going to associate to little g? Well, you know, which one? Why would you choose anything else? Surely that's the most natural, the most canonical coset to associate to the element little g. To choose anything else like g squared or g inverse or some other thing related to the element little g would be you know, more complicated than it needs to be. Okay, so that's the canonical choice. So this mapping phi here is the kind of obvious canonical way, the most direct, plain and simple way of mapping homomorphically a group onto any factor group of it. You just associate every element with whatever coset it generates. This eta we're going to define now as well. The map eta is a map from the factor group to an image of G under psi. And again, it is quite canonical as well. So how do we define value? How do we define the map eta? Well, it's defined on the factor group. So we have to be able to define it on the elements of the factor group. The elements of the factor group are cosets of the kernel. So a typical coset will look like little g times the kernel psi, won't it? Yeah, that's a typical element of the factor group, an element of the group times the kernel. And we want to, in some nice, obvious way, associate to this coset an element of what? Well, an element of phi of G. This is a subgroup of H, and it's the image of psi of G. It's a subgroup of H. It's the image of G under the homomorphism psi. So which element can we choose, which is obviously an element of this subgroup of H, and which is somewhat quite related to this coset, little g. Well, so you start to think, I have to be sure that it lives in psi of g. So it has to be psi of something. It has to be psi of something that's come from the group G. And I want it to be related to little g. So what's the most obvious element? Psi of little g, yeah, which is psi of something. So it obviously lives in psi of g, and it's related to, it's mapped from, it's somehow connected to this coset. It has to be psi of g, doesn't it? Now, what needs to be proved, you know, the detail, some of the detail, the missing details here are proving, well, first of all, I think in the proof they spend some time proving, or does he does it, well, he does it kind of in the preamble to the statement of the proof, proving that the canonical homomorphism phi is indeed a homomorphism. This got defined here, phi here in relation to the kernel of psi, but it's, that definition makes sense no matter what normal subgroup you're talking about, no matter what factor group. So we might need to just, okay, I've claimed it's a homomorphism there, but we might need to hammer that out and actually prove it's a homomorphism, prove that it satisfies the homomorphism property. And you also, technically, you also need to, prove that it's a homomorphism, and prove that, now there's a couple of things about eta we have to prove. We have to prove it's an isomorphism for sure, but even before that, you see, we have this well-defined problem here, or this well-defined issue. Technicality raises its head, because look, eta is supposed to be a function on the factor group. The objects in the factor group are cosets. But now the formula I've given here says, okay, define eta on this coset here by setting this coset to psi of little g. But now, in order to be able to make that definition, I have singled out a representative little g of this coset. But now, cosets, remember, are formed by gathering loads of elements together and clumping them together, considering them as one object. I've just picked out one of those elements, little g. The issue is, supposing this very same coset was represented by a different element, little g, a little g prime, then you'd be forced to say eta of this coset is equal to psi of little g prime, which potentially looks like a different element to psi of g. So that would be a problem, because that would mean your function isn't well defined. It depends which way you represent this same argument. Maybe you're trying to give it different values. The point is, and it shows you what you have to prove then, if you take any other element representing this coset, so some little g prime, which is the same left coset as this, that actually psi of g prime is the same as psi of g. So it just looks like a different element, but in fact it's the same element. Psi of g is the same as psi of g prime. G and g prime, despite being different elements in g, get collapsed by the homomorphism psi onto the one element, psi of g, or it's also called psi of g prime in H. So that has to be shown first. We have to prove that psi is in fact well defined as a function, so it qualifies as a function to begin with, and then prove the isomorphism. And then prove it's an isomorphism. Okay, but those are technical details, and I'll leave you to read through those. If you've got any questions about them, please do bring them to a future session. Well, I just wanted to explain this theorem just on this level. Okay. Now, this diagram I've mapped out is a nice example of what mathematicians call a commutative diagram. These come up a lot in algebra. What a commutative diagram is, so in algebra, when you have a load of different algebraic objects, different but related, and you draw them all on the page and you draw in mappings between them. Okay, so here I've got three objects. I've got the groups G, the group H, and the factor group G mod the kernel of psi. I wouldn't call this a fourth different object because this is a subgroup within G. So this is part of G. This is a subset of this set. So you've got these three different groups, G, H, and G mod kernel of psi. You've got these mappings, psi going across the top, phi coming down here, and eta going across here. When we say this is, so what we like our diagrams of algebraic objects and maps between them, we like them to be commutative. And commutative here means that if you start at the top left in G, and you zip along here under psi and you go to H here, but there's an alternative route to get to H starting with G. You can also come down here and then go across here. Okay, this lands you in this object, but this object is a subset of H. So this lands you in H as well. These two different routes going along psi or along eta after phi, so phi first and then eta, that those two routes are the same. The same function. Okay. So a commutative diagram, i.e. the function psi is the same as the function eta after phi. Okay, and that's what we like our diagrams to be in algebra. Okay. And building commutative diagrams of maps between related algebraic structures, that allows you to study kind of all the interdependencies, the links between the different objects. Okay. So what that first isomorphism theorem tells us is that for any homomorphism, okay, psi might not be injective. So let's assume we're talking about a genuine function that is not an isomorphism. So psi is not one-to-one. So it does lose some information about G. H, we have this subgroup psi of G. It's the homomorphic image of the group G. It possesses some of the group properties, a kind of simplified form of the group properties of G. Some of the structure of G has been lost because we've gathered together elements in G and collapsed them down onto the same image in H. Okay. But yet there might be something of the group structure of G surviving in psi of G. Okay. But we would typically expect psi of G to have less subgroups than G. Yeah. Some of the distinct subgroups that are over here might have been collapsed on top of each other if you look at their images in psi of G. So what this first isomorphism theorem does is it gives you a way to exactly capture exactly what the group structure is here in terms of stuff you can build out of G. Okay. And what you do is you use the kernel of the mapping psi, so the kernel of psi, that's a normal subgroup within G. We said the motivation for it at the start was that the kernel captures the fact that the mapping psi is losing information about G. It gathers together all the stuff which is collapsed onto the identity. So it somehow measures or quantifies the loss of information under the homomorphism psi. So we have this normal subgroup kernel of psi, and when we factor out G by that, okay, we look at the cosets of that, this group, with this factor group, which we're able to build out of G using only information about G, well, information about G and the mapping psi, but it's built directly out of G. But this then is an isomorphic copy of the image of G. Okay. So whatever's going on with this subgroup of H, going on in the group H, whatever group structure there is here, is we can see isomorphically going on in this factor group of G. Okay. Now, maybe a good thing having seen that, our first example of a nice, not too complicated commutative diagram, is just to show you, what more advanced algebra is like. I haven't prepared this. I'm just going to do it on spec. But if you do a Google search for commutative, hang on, just get this so you can see my screen. Can't see my screen. Well, you can see that screen, but hang on. Extending. I'm going to mirror the screen. Okay, you can see that. Good. So if you just Google the phrase commutative diagram, look for images. Okay, so R1 only had 3 objects in it. Let's just try and find the most complicated one we can pick out. But you get the idea. The study of advanced algebra is to study, complicated sets of algebraic objects and to look at, all the mappings that are between. Even this one, it kind of makes sense to arrange it in 3 dimensions. So this diagram is best thought of as a diagram of objects in 3 dimensions. So you have some kind of chain of algebraic objects here, A, B1, C1. I mean, I don't know what they are. You need the context of defining what kind of objects they are. We have all these different maps going between. You've got zeros here, which are trivial, representing trivial instances of these algebraic structures, whatever they are. And this would be a commutative diagram. So if you want to go from A1, from A1 up here to C1 prime, you've got several different routes. You can come down here and then go all the way across. You can come all the way across the top and down there, or you can do this kind of dog-leg journey. All those different routes through the diagram would all be the same function from your starting object to your ending object. Okay. So building commutative diagrams it gives you a systematic way to study the relationships between all these objects. And you'll find ones that are even more complicated than that. Some of them get quite fantastical. What about this one here? Yeah. They even struggle to fit them into 3 dimensions sometimes. So you can see quite sophisticated stuff going on. So be thankful we've only got our nice simple ones. Okay. All right, I better finish there.